This is the Amp Hour Podcast, recorded December 16th, 2014. Episode 228, with guest Shahryar from the Signal Path, Quisquous, Quivering, Quadripole.
Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
And I'm Chris Gamble of Contextual Electronics.
Hi, and I'm Shahryar from the Signal Path.
Hey, Shahryar, thanks for joining us.
Well, thanks for having me. I appreciate it.
This is the first time we've
test
chatted.
equipment greats mashing together on the Amp Hour. That's good.
Yeah, I'm really excited. I've been looking forward to this for some time now.
Awesome. And tell us what you do for those who don't know. I'm sure everyone's seen your video blog, surely.
And if they don't, they should go and pause right now and subscribe and go watch videos and then come back.
Because they're pretty
thanks,
awesome.
I appreciate it. Yeah. No, well, I do basically two things. Professionally, I'm the ASICs design manager, technical manager at Bell Laboratories, which is part of Alcatel-Lucent. I work here in the US in the Murray Hill building, the famous Murray Hill building where the transistor was invented and the laser was invented and so on. Cool. And I do ASIC design for whole different kind of applications, millimeter wave transmitters for wireless and for wireline of optoelectronics and so on. And at the same time,
so you're in the whole group. Sorry, you're in the whole. So you're like ASIC for the entire Bell Labs. I thought you were more like a specialized in one group or something, in sort of like the RF millimeter wave.
Yeah, so Bell Labs has a few places around the world that works on ASICs specifically for these very, very high-end applications. So for us, in our Murray Hill, New Jersey building, we are a reasonably small group because we do very specialized type of work. But yeah, I run that team here. Is about 6 of us or so, and we design ASICs for crazy stuff. We do crazy things.
Only 6 of you design the ASICs.
Yeah, we do more. There's only 6 of us. We're trying to expand our group. Actually, you'd be surprised how hard it is to find millimeter wave designers.
Once you ask on the Amp Hour, it's not hard at all.
Oh, okay, perfect.
Yeah, Dude, I know. This is pretty specialized.
Looking at these papers, I'm like, how many gigahertz? That's a lot of gigahertz.
Terahertz, dude. Terahertz.
Yeah.
Not this gigahertz rubbish. That's DC. Gigahertz is DC to this guy.
Yeah, gigahertz DC. Yeah, that's true. It's funny as we say that too.
Really? Oh, Jesus.
Yeah, it's a famous thing that people doing millimeter wave always say. And my old supervisor at my university used to say this. Gigahertz, that's DC. What is that even worth talking about?
I love it.
Good Lord.
Oh, goodness. We've entered another stratosphere, folks.
Oh, man. I don't even... So like, what are some of the geometries and stuff like that you have to use to get... Like, what is it? What is the magical bits that make an ASIC go that fast?
Well, generally they refer to kind of work that I do as millimeter wave. They typically refer to anything above 30 gigahertz as millimeter wave simply because the wavelength becomes less than 10 millimeters or so. So that's why they call it that. So the frequency range that I work, somewhere around, let's say 100 gigahertz, there the dimensions are really, 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 really small. So in silicon, you're talking about hundreds of micron for wavelengths, basically.
Oh, wow.
So
okay.
I believe at 1.6 millimeter would be 90 gigahertz in silicon with a dielectric constant of 4.2. So that's kind of the dimensions you're looking at. Now, the thing that makes devices work that fast is simply has been due to scaling. So the devices have scaled as time passes. Their intrinsic parasitic capacitances and unwanted components as part of the device have shrunk down and become so small that the devices become really, really fast. So making a transistor that it's capable of generating signals in the hundreds of gigahertz is now a trivial matter.
Trivial
by the standards of the state of the art silicon process.
State of the art, you're talking terahertz, right?
Yeah. So even if you look at what Intel makes their processors out of, Intel, the next generation processors being made, in 22 nanometer, 14 nanometer, 14 nanometer CMOS process. Those devices themselves, each individual one has an FT, which is the maximum current gain of a device in the hundreds of gigahertz, 200-300 gigahertz easily.
Right.
But of course, a microprocessor is a very complex structure. That's not going to run at that speed. But if you were to make analog circuits, if you give me a state-of-the-art CMOS process, I can make you an amplifier that works at 100 gigahertz.
And that would be like a commoditized hundreds of gigahertz transistor kind of thing at that point, because
it would be. I mean, if you just give me a basic CMOS process, basic 22 nanometer CMOS process, making a 100 gigahertz amplifier out of it is possible. I'm not saying it's easy, but it's possible, and it's already been demonstrated.
Wow. Can you do that? Can you make a flip-flop, for example, like a single flip-flop that works at several hundred gig? Is that, or is it purely the analog domain?
No, you can. In fact, published a paper back in, I think it was in 2000, and it was a long time ago, maybe 6 or 7 years ago. That was an 81 gigabit per second retimer, which is a flip-flop. But that flip-flop doesn't look like a traditional CMOS flip-flop you would see with digital, zeros and ones. It's a CML type circuit, which is a current mode logic type circuit.
Yeah, right.
Yeah, so that works at 81 gigabit per second. That was in a 65 nanometer CMOS process. Right.
So you couldn't actually get a real, in quote marks, digital flip-flop, like even at a low voltage level, like with a 0.8 volt, 0 to 0.8 volts or something.
I would imagine that for something like that, with a 0.8, if you go to state-of-the-art CMOS, you probably can make a 10 to 15 gigabit per second flip-flop using regular CMOS, probably if you hand lay it out, custom lay it out yourself.
Got it.
Yeah. I think that's possible. I've never tried, but I think that's possible.
That's awesome.
So there's the upper limit, folks. That's probably that's why these Intel processors still work at 2, 3, 4 gig. Because, as you said, they're incredibly complex, right?
Yes, they're extremely complex, and they have thousands of digital lines where you have to meet specific timings on. So that's what limits your speed there. Maybe you can make one individual flip-flop or 10, 20 of them, so on, run at 10 gig, but to build a system out of that is a whole different problem.
With a billion
devices, it's a very different problem.
You only have to, if you run away from a bear, you only have to be faster than your slowest friend kind of problem, right?
Right.
That's true.
Now, you're like an expert in this, ASIC, high-speed, gigahertz, hundreds of gigahertz ASIC area. Does it still impress you that Intel are able to actually design and lay out these, a billion transistors operating at 4 gig?
Yeah,
that's child's play.
Oh no, not at all. It's definitely not child's play, because the complexity of such a system alone, just to be able to design and simulate and create such a massive system is extremely impressive. And obviously, this is an evolutionary work.
Oh, right. Of course,
it obviously didn't get there in one day. It took many decades, but the issue of having a billion devices, that's a yield issue. Once you build a billion,
for starters, right?
Then you run into this idea of being able to actually build that many devices that work. I mean, there are some redundancies and so on, obviously, in there that allow some percentage of yield to be acceptable, but it's extremely impressive. The lithography dimensions, a device, a CMOS transistor at 22 nanometer, for example, is a far more complex device than it used to be when it was a 0.35 micron device. Everything about it has changed. It's how the physics under which goes into it is far more complex. They have a whole variety of different types of elements that go into it. The CMOS transistor is almost barely is made of silicon anymore. It has so many other things in it. Yeah. So they have germanium, and they strain the channel, and they do just crazy things. And the lithography itself is ingenious, and it's very tough. And there's only really two main players in the world, or 2 or 3 main players in the world that do that kind of stuff. Is Intel. Used to be IBM, which now lost its foundries, unfortunately, and there's STMicroelectronics.
Right. They sold them, didn't they?
No, they actually paid to give it away.
Yep. Oh, that's right. Yeah. Who actually got those in the end? I think
Global Foundries took it.
Yeah, well, it was Global. Yep.
Yeah. Global Foundries took. I think they paid $1.5 billion to give it away.
And Global used to be AMD's foundries, right? Isn't that right?
Yes, I believe so. Yeah. I'm not sure now who is. Maybe it's TSMC now. I'm not 100% sure who makes their digital circuits now. But
who's the third one?
For the is Intel ST Microelectronics, which is in a company in France. They have a state of the art ST Microelectronics. Yeah.
Oh, okay. I didn't know they were that state of the art in the silicon space.
Yeah. They have
in the
the
wafer manufacturing space.
Yes. They have some of the most advanced silicon germanium SiGe by CMOS process. Actually, they have the most advanced SiGe by CMOS process in the world.
I did not know that.
Okay.
Yeah.
So who makes your stuff? You know, you've come up with a new circuit. You want to circuit, you know, like, geez, like you're soldering some axial resistors to an FR4 board. Like, anyway, you've come up with a new circuit.
Do you have a kit we can build in the 10 gigahertz kit?
Yeah, but that demo is set up in our lab actually. But for the stuff that I published, I can tell you that it's because it's in the paper already. It's done by Tower Jazz, which is an American company. Yeah.
Oh. Yeah, never heard of them.
And it's an American-Israeli company. It was Jazz Semiconductors, and they kind of combined with Tower, and they became Tower Jazz, and so on. They have their own history there. But yeah, they've
got their own wafer fab.
Yes, absolutely, and they make the wafers. And one of the reasons why some of our work is with them is because it's a certified process in the US. So if we make stuff for the government, for our government customers, and it cannot leave the country, so it has to be manufactured in the United States. So we can't go and use somewhere in Asia, for example. So
got it.
Yeah.
Got it.
That's cool.
And of course, the government have their own wafer fab. NSA, hi to the NSA who's obviously listening in. They've got their own wafer fab.
Well, and they download the FR.
Yeah, I don't know. The government has historically been very focused on 3.5 indium phosphide and gas type devices because they, for making radars and amplifiers and weaponry and things like that, those devices have been traditionally used because of, their properties and so on. So they have the United States has rather advanced 3.5 and gas processes for that reason, even though we don't make microprocessors from them, we kind of have handed that market to Asia.
What is that actual 3.5 in gas? What is that process?
Oh, the 3.5 refers to the elements used in the semiconductor being from the third and fifth group in the periodic table. So indium phosphide, gallium arsenide, those type of material.
Oh, right. So they're a group of elements.
Exactly.
Got it.
Yeah. So that type of semiconductor has certain properties that distinguishes it from, let's say, CMOS or silicon germanium. Indium phosphide and gallium arsenide and gallium nitride processes have very, very high breakdown, and they are very, very, very fast. So you can make really high power amplifiers at high frequencies with them, but you can't build very complex circuits from them. You can only make very rather simple circuits from them.
Is that because of why is that? Why is that limitation?
That limitation is part of the processing limitation of this type of process itself, where the yield will become extremely poor if you start making very complex devices with them.
As in large or just physically small?
Both physically large as well as having many devices in it.
Right.
Yeah, so the yield will drop, so you can't make anything with it.
Yeah, there's not as much research into that because there's just not as much volume. That kind of is weird that, like, you get to play in you're doing some CMOS, but you also said you're doing gallium arsenide stuff now too, right?
No, I actually haven't done any gallium arsenide, but don't underestimate them because you cannot buy a cell phone without those type of amplifiers in it because you cannot make you cannot make an amplifier to transmit the type of power you want in silicon easily. There's actually, as far as I know, there's only one company in the world that's ever produced PAs for cell phones in silicon, in CMOS, and that's a very specific niche thing they've done. Every cell phone you buy, every Wi-Fi chip, everything that you have eventually that does this transmit as this type of power, you need those devices. You need those type of PAs in those exotic material.
Are they silicon on sapphire? Because we do that here in Australia. There's our only wafer fab here, I think, specializes in silicon on sapphire RF stuff.
Yeah, that's another very, very niche type of application, silicon and sapphire. I haven't done any work with it at all myself. I just know that the wafers are really pretty because they're transparent.
Oh, cool.
Awesome.
Yeah, because they're on sapphire. But I haven't done any work with that. That has its own very high breakdown material. So you can, again, if you want to make let's say a a 10 watt amplifier, right? A 10 watt amplifier into 50 ohm is going to require signal swings that are multiples of the power supply CMOS even has to begin with. So obviously your devices will break down long before they would ever be able to produce such power.
Okay.
So you need a device that has 10 volt breakdown, and the breakdown of a deep sub-micron CMOS device is 0.8 volts. So you can imagine why the limitation is there.
How many broad groups are there of manufacturing technologies for, chips in general? Is it like dozens and dozens and don't even ask, or can they just be broken down into like 3 or 4 major process technologies?
Yeah, I mean, they would typically be broken into mainly 3. There would be all the CMOS. That includes regular vanilla type CMOS, which is very basic bulk CMOS, and then it would be FinFETs and so on, and then under that category you would have silicon and insulator SOI process and so on. So that would be all CMOS. And there is silicon. Okay. Yeah, there will be silicon germanium, which is still a silicon process, and silicon BiCMOS, which is a combination of silicon germanium bipolars, as well as CMOS. That would be, I would say, another. It would still fit under silicon. And then there's a whole 3-5 category, like I said, gallium nitride, gallium arsenide, indium phosphide.
So there's CMOS 3-5?
Yeah, there would be a CMOS 3-5, and I guess you could say SiGe BiCMOS. But really, it's just silicon and 3-5. That's what you can do.
Right. Okay.
And there's also this whole carbon nanotube stuff, which of course is another thing on its own, but that we don't have really any main circuits with those yet. They're really research experimental, but they're promising, but experimental.
Yeah.
Right. How long does it typically take to go from promising to you can buy chips?
Honestly, that depends on what you can sell with it.
Right.
I mean, the only reason CMOS is where it is because we continue to demand more from our electronics. We demand more storage. We demand more processing power. We demand lower power. So they keep scaling CMOS aggressively because there's a lot of money driving it. If you remove the driving behind it, obviously nothing will happen. So that's basically really what it. I mean, there's obviously some physics involved and there's some limitations, and even with CMOS too. Once you hit about 8 nanometer devices, and you have to perhaps do something different. Although people have been saying this for 10 years,
right.
But there's the cost also is another issue. The fab cost. This whole Moore's law business they have.
We were going to ask about this. Yes.
Yeah. So there's a
Tell
whole.
us, is it already over?
No, I don't think it's over. You got some time still to go. But if you think also, there is also a paradigm shift here, right? So at some point, again, everything is economical at the end of the day, and then the physics also play a role in that. So it's true that you have this doubling of processing, computation, and circuit complexity every 18 months or so, but the fabrication cost has the inverse slope of that. So the fabrication cost of deep sub-micron CMOS process is also doubling, going up very, very rapidly. So these things do become extremely expensive to manufacture. The only reason you can go out and buy the next Intel processor in 22 nanometer, 24 nanometer, pick it up for a couple of $100 is because the market is absolutely massive.
Right.
If you want to if you want to go right now and do a tape out, which is what is referred to submitting your design for fabrication, and you want to say, I want to tape out in state-of-the-art CMOS, you're looking at $3 or $4 million for one mask set.
Yep.
So one wafer, right?
Yep.
So that's the kind of, and that the fab to be able to produce that would have cost $2 billion to make.
Oh, I think Samsung just announced
yeah.
a $10 billion one. They just announced $10 billion for their newest one.
Then that's because this has a huge capacity, enormous capacity, and Samsung is in the memory business essentially. So what is driving it is that they want to put more and more and more memory.
Right. So that's the reason it costs so much. Is just because they've got a larger throughput, larger capacity, rather than the technology itself.
Yeah, I would imagine that a $10 billion fab is not simply $10 billion just because it's the state-of-the-art CMOS. I think you can probably make a fab less than that, but it must have an enormous capacity.
Oh, yeah, it does. They're building a whole new city around it, basically.
A whole
South
city,
Korea.
That's crazy.
I mean, they provide memory chips to everybody. So, I mean, all these SSD drives, I mean, how many years did it take for SSDs to essentially become the de facto? I mean, that's the driving force behind it. So that you can imagine if that's how fast it grows, that's why Moore's Law is where it is.
The amp hour server is now on an SSD drive somewhere in New York. So
Yeah, perfect.
Servers drive a lot of stuff. What about the actual... When you do research on this kind of stuff, I mean, this is awesome. Do you basically have to dig into, like, the design packages and, like, kind of start tweaking stuff and simulation, or how does that stuff work?
So generally for analog design in general, this is probably true. And for millimeter wave design, there's some extra complexities that comes along with that. But normally, if I were to get a design kit that I have never used before, let's say a new technology.
A fab? That's like a design kit?
Yeah, the fab will provide you with the design kit, and after you've signed the appropriate NDAs, then they give you the design kit, and then as a designer who's, let's say, hasn't used this new technology, you start experimenting with the devices, see how fast they are, simulate their FD and their Fmax, and look at their layout and how complex they look, simulate some of their critical analog and RF performances, and then you start creating blocks that you want to do certain things with. Let's say I want to make an LNA, a low noise amplifier, or I want to make a PA. Then I go ahead and put together one and then start tweaking it and playing around with it. But when you start doing things in millimeter wave design at 90 or 100 gigahertz or even above that, then you're starting to run into some really weird things that devices do. So all their imperfections are now right there, and you have to, if you don't model them. One of the things I did when I was a student a while back is that I designed this 160 gigahertz PLL. It's a phase lock loop that has an output at 160 gigahertz. Is intended for use for medical imaging.
Okay.
So at 160 gigahertz, a metal line that you draw, anything that you draw that's more than a few micrometer in length is now an inductor. That is very important.
Yep.
Right?
That is so cool.
So you have to...
No, it's not. No, it's not.
I mean, it's not. I'm just saying, what I'm trying to say is physics rocks, unless it's stopping you from
physics
graduating.
Physics is a pain in the ass, Chris.
Yeah. I have made capacitors in silicon that have a dimension of 3 micrometer by 3 micrometer. That's a capacitor.
And how many puff is that?
That's usually, that would be, depending on the metallization, that's something around the order of 12, 15 femtofarad.
Femtopuff, yep.
Yeah, so 0.015 picofarad. Yeah. Very, 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 very small.
Nice.
Yeah. So, I mean, and that is a if you calculate the impedance of, let's say 10 femtofarad at 160 gigahertz, is significant. It's right there. It's what you would need to match an amplifier to 50 ohms. That's all you might need.
Yeah.
Yeah. So
that
is so crazy.
This is ridiculous.
Yeah. So these things start to become. So we do complete 3D EM simulation with specialized software to electromagnetically fully simulate these components up to those frequencies before we put them back in the design and model them. And because all these are custom hand drawn and hand laid out, the process is iterative and time consuming, because you draw something and then you simulate it and you go back, put it in the circuit. Now you find some result and you go back and you change it. You do this over and over and over again until you get what you're looking for.
Now, I can imagine that the software tools and the simulators are actually there's more probably more science that goes into those than the manufacturing technology. Would I be wrong?
Well, there's certainly, I'm not sure if it's more that goes into manufacturing. Yeah, I completely agree that they're extremely complex, but the only reason I'm reluctant to say that there's more in there is because manufacturing covers several classes of science at the same time.
Yeah. Oh, of course. Yeah, right? I know. So it's a totally different ball game. You can't compare them, really, but...
Yeah, but it's extremely expensive.
Ridiculously because how many people would they have working developing those?
I mean, huge. I mean, if you look at Cadence, right?
Yeah.
Cadence is enormous, and they are really the only player in this game where they do complete top down.
Oh, really? The only one?
Yeah. If you want to do complete top down design, meaning that if you want to be able to do transistor level layout all the way up to full system simulation, Cadence covers that entire range.
Wow.
So that's why they are the de facto software in the industry, right? And most people use that. But even for a group of, let's say, 5 or 6 designers, our CAD tool costs are, maybe $300,000 or $400,000, maybe even $500,000 a year.
Yep.
I'm surprised it's that cheap, actually.
Yeah, I kind of. Yeah.
Seriously, because there's,
That's only cadence. That's only cadence, simulation, layout, and EM. Yeah.
Yeah. That's bonkers.
Yeah, it's very,
because I can't imagine
expensive.
how many people they've got working on those.
Oh my God,
tools,
it must be huge.
And are there, like, do you find bugs and go, well, look, this just, look, this simulator said it worked, and we paid $3 million for our bloody solder mask, and we made our chip, and your simulator's wrong. Is that?
Well, that's it. No one's going to take responsibility if your simulations are wrong. Design kits change all the time, especially if you design something at 2 gigahertz. Okay, and by now, let's say you pick up a fairly advanced silicon germanium process, let's say, and you design something at 2 gigahertz, it should be really, really, really well modeled. But if you start using those devices at 100 gigahertz, now you have to give the foundry a little bit of a leeway, because they can't really completely model those things really well at 100 gigahertz. First of all, measuring a device up to 100 gigahertz is very difficult.
Yeah, it's hard enough. Yeah.
So it's kind of it's a designer's responsibility to appreciate the limitations and work around them or build around them or take that into consideration. But we've had fairly good matching between simulation and measurements. You can see that in some of my papers too, because we show both. It's if you do good modeling, good simulation, good extraction of parasitics with the devices and all that, usually pretty close up to 100 gigahertz, I would say.
Do you ever get to see the release notes on when the design kits change? Is it like, we did testing,
for sure.
but Morty was standing in the room, and we didn't think he was standing in the room, so now it's a different...
And somebody farted in the next room, and it's...
No, they
and
do tell you.
All wrong.
No, they tell you that, hey, we remeasured some things, and we found this, and, here's the new model. And you go and simulate and say, damn, everything's different after things change.
Wow.
It's happened before, but normally, you have to keep in mind, once you start working with these things, you also, I know it seems like a kind of like a black hole where you don't know what's going on, but you tend to develop an intuitive understanding of what things are probably limited on the modeling side. So you take that into account. So you know that some things, let's say the transconductance of the device, the GM of the device, that's probably accurate. That's a DC characteristic. That's a DC property.
Yeah.
So that's probably accurate. But, let's say the capacitance, the exact capacitance of the collector of the device up to, down to 0.1 femtofarad at 100 gigahertz, maybe that's not so accurate.
Yeah.
So,
Right.
Man.
So you work around, basically. But yeah, you're right. I mean, it does end up being a challenge.
And those simulator tools, they would be an evolving process, of course. Like, when a new manufacturing technology comes out, a new process technology, I can sort of imagine the models not being that accurate. But over time, they would build and build and build, and
yeah, absolutely.
You'll build up more trust in them over time.
Yeah, absolutely. I mean, a brand new design coming out, a brand new technology coming out is always going to be risky the very first time you design it. For sure.
Right.
And of course, typically also when a new design kit comes in, especially in CMOS, the very first thing that comes out is the digital design kit intended for digital synthesis, which is what the whole process is geared toward. And then after that, the analog performance of the devices become refined and better, and then eventually becomes an RF process as well as a digital process. This is normal and happens all the time in state of the art. That's one of the reasons sometimes manufacturers are reluctant to build something, especially an analog circuit, right off the bat in the latest technology, because it is a little bit of a gamble where you don't know exactly. And then by the time the process matures, the models become better. Right. And then you can count on them.
And that benefits too, because the manufacturing costs usually could drop a little bit because you start using older technologies for
absolutely. Yeah,
stuff.
It's always at the deep submicron, the very, very latest technology is always on that exponential price curve.
Yep.
Where we're going down one technology node will double or triple the cost, but it wouldn't necessarily double the performance, but it will double the price.
Right.
So who develops these models? Is it the fabs?
The fabs do,
themselves?
Yeah. Yes, the
right.
fabs do.
So, this is the thing that's always puzzled me. How do they develop these models and test them against an actual manufactured wafer when it's like $3 million a pop? to do a mask, or is there a sort of a quick, cheap process they can use to sort of spin a little test circuit to check their models?
They are in the business of creating. They're in the business of creating a process. So for them, the cost of creating experimental processes internally, where they tweak all the knobs and tweak all the compositions of the devices in order to get what they're looking for, is part of the development cost of the whole thing. But but they do exactly what you're saying. They come up with a device architecture, device physics, which is an evolution on the old one. They scale it. They make all the changes they think is necessary, and they do several different runs, different corners, and different process splits of what they think will happen. They have some models, which is also the evolution of the old model, and then they do some measurements and compare them with the models, and they tweak the models and so on. These models that I'm talking about for process like CMOS and silicon germanium or so, they're different types like BSIM models and so on. These are standardized models that plug into the simulators. So everybody has to create them. So the foundry will have to do that if they want to basically sell their process as something that anyone can use. So that's a typical thing. And they do that over and over. And once they're happy with it, they release it, and then once they're really, really happy with it, then it becomes a production run where basically everybody starts using it. But if you're doing research, you typically, when I was at university, I had a really good opportunity because both of my supervisors actually had really good relationship with foundries because they were really good at what they did, and foundries typically gave us experimental process before they were even released, long before they were released.
Nice.
And we would make some state-of-the-art record circuit in their process, and there will be a feather in their cap and say, look, our new process, somebody built 160 gigahertz PLL in it, or somebody built a whole 200 gigahertz sensor in it, and you look what our process can do. So it's a mutual relationship from that perspective.
Yeah.
Got it.
First time for free, next time you pay.
Yeah, that's the nice thing about, and this is another reason why it's so hard for me to find millimeter wave designers is because to be trained to be a millimeter wave designer is an extremely expensive thing, and not all universities even engage in. There's only a handful of universities around the world that do real millimeter wave design, where the students, make something at 100 gigahertz, measure it, and it's their thesis. And then they come out and they have now an experience which is really rare, and it's very hard to get those people to, it's hard to get them to come to New Jersey for one thing. It's also hard, to find them. Yeah, no, for sure.
So how did you get into this? Did you just stumble upon it, or did you go, I want to go to that university because I want to get into millimeter wave, ASIC design? How did you tell us the story?
Well, when I initially moved to Canada, which was about 20 years ago or so, then from Iran. I was born in Iran. Yeah. So then I moved to Canada, and, being a wonderful country that it is, accepted us as immigrants and then as citizens. And so then I went to University of Toronto for my bachelor's degree. I actually did my bachelor's degree in computer engineering and not in electrical engineering. Right. And then I switched to electronics in my master's, and then finally my PhD. And like I said, part of it is indeed luck that I happened to start working with professors who were into very, very high-speed millimeter wave design. And once I kind of got a taste of it, I didn't want to do anything else. And so I got involved in doing that, and I started working on millimeter wave data converters many, many years ago, and that ultimately became my PhD thesis. And then while I was finishing my PhD, I did an internship at Bell Labs because our director, who back then used to do what I used to do, he was technical manager when I was doing my PhD. He invited us, a friend of mine and myself, to be an intern. And then we did our internship there, and it was very exciting to see doing research, especially because at those times, there were very few places left in the industry that actually did research at all. Yeah. Because of the problems of the economy. That's the very first thing that goes, right? Is the research is the thing that goes. Yeah. So Bell Labs is one of the very few places left that you could do something like that. And then and also you could publish. And I really wanted to do those things. And that really kind of got me to go back and be there and engage in this type of research and be able to work on, one day I work on phased arrays, and the next day I work on circuits for optoelectronics, which are really two ends of the spectrum as far as ASIC design is. So it's very exciting to be able to do that.
Could you explain the difference between those two and why they are so different real quick?
Well, because one is essentially for wireless applications, doing phased arrays, completely a wireless system these up converters and down converters. Very, very different than what you would build when you want to build an optoelectronic circuits for optical communication, where you have CDRs and TIAs and drivers and so on, where you're doing a very, very different type of circuit. One is a broadband application, one is a narrowband application.
Oh, okay.
Very, very, very different design and quite different systems. In fact, I mean, there are obviously a lot of commonalities, but
I was going to say, it's still things moving fast, right?
Yeah, I mean, you can think about it in terms of somebody designing a circuit for a USB 3.0 chipset versus somebody designing a circuit for a Wi-Fi chipset.
Right.
Yep.
Right.
Quite different.
And you were talking about the research side of things, how that's the first thing to go.
Yeah.
Like, do you find that, well, governments are probably too stupid, but, like just in general, people are realizing, that was like a mistake. That was a bad thing. So do you see like research coming back into the country, or
it is a shame. You're
people
right.
just don't care?
Yeah, well, the reason research goes out of the door right away in many situations is not necessarily because the people who make those decisions don't appreciate the importance of research, but it's because the system under which the performance of these things are evaluated, and these systems are typically short-term.
Mm-hmm.
Yes,
so,
always.
And so if you want to meet a bottom line at the end of your quarter, if you cut $3 million from research, that's going to look good, right? But it's not going to look good in 5 years. It's certainly going to look good in 1 year.
That's right.
Yeah.
So in some ways, you're forced to do that in order to be able to meet a certain thing. And in some other cases, some other companies, it might very well be the difference between going under or being able to actually survive for a little bit longer. So it's difficult to say what is what. Bell Labs has this long legacy, and if you were to cut Bell Labs completely, you might save money, but because it has such a long legacy and because it has such a big impact and has such a big name associated to it, it would actually damage Alcatel-Lucent quite a bit.
Totally.
Yeah, so obviously nobody would think of it, and Bell Labs produces so many patents and so much technology and has such a history of doing that, from many different categories, not just from silicon. We have physics discovering the cosmic background radiation. We have software, Unix, and so on. Then there's lasers and transistors, and a whole bunch of different things. And so you don't want to get rid of them. That's why I love Bell Labs. You always in one way or another.
Well, you hope, because you could have said the same thing about IBM, right? And they just pissed it away.
Yeah, I can't argue. I can't argue with that completely.
IBM had almost as big a reputation as Bell Labs in terms of research.
Yeah, I mean the TJ Watson Center, which some of my colleagues from my PhD were there. Yeah, I mean it has and I'm sure they will continue to do work. But it really is a shame where their process, the way what happened to their foundry situation, and it's all finance. It's all finance.
Yep.
Yeah, at the end of the day. But having said that. I was thinking before we were going to record, I was thinking about this whole idea of having this access, and given everything that's happening, I was reflecting on the fact that right now as we speak, there are places in the world where children are regularly killed for wanting to pursue education, and at the same time we have here and other places in the world children that have the entire collective human knowledge at their fingertip. Yep. This is an absolutely inconceivable gap between these 2 points, and the only way that gap is ever going to go away is by creating education, by making it more available, by disseminating this knowledge. And this is a really big part of what you do, Dave, and what other people like you do as well. Because I think a good education system is probably one of the greatest human inventions that we can ever think of. And it's
totally agree.
And this whole this research, and there's all these things tied together from my perspective to be such an important part of who we are as a species, not just as researchers.
Hence why your video blogs are almost 100%, sort of educational focused.
Yeah, absolutely. I mean, the signal pad, obviously, my attempts at creating that has been my way of giving back to the community, has been my way of being able to show and express my, not just what I know about the subject, but also my passion for the subject. This to give somebody a great gift to give somebody is this sense of curiosity, is to want to know how things work. Things are just so much more beautiful when you understand how they work. And this is my goal for the signal path, and the time and the effort that goes into it. Obviously, as you know, and I have a whole new job, so for me, the signal pad kind of always loses money, so it doesn't really it's not intended to make money. So it's not a financial endeavor by any means. And I'm privileged to be able to do that. I consider myself highly privileged to be able to have the resources and the time and the people who support it and enjoy it so much to be able to give back to the community in this way.
And how long does it take you to produce one of those, educational videos? I'm talking about, ones with, you set up all the elaborate tests and the test gear and the test plans and all the documentation and everything else.
Yeah. So usually I think about what I'm going to do, either when I'm driving or when I'm taking a shower or something like that. I usually build it up in my head first. But if I were to talk about specifically the time invested in making it, I think for every 1 hour of video that's produced, I think it takes about 6 hours to go from the recording it and then putting it up on the website and writing a description, making a documentation. It's about 1-to-6 ratio, I think.
I would have thought it'd be more than that, because some of your test setups are quite elaborate. Yeah, I have to write software, you got to draw documentation. And
the test itself, I kind of conceive in my head. I'm not counting the time, driving around thinking about it. Yeah. So that part is not there. But also, I'm really, really used to building setups all the time. So I have an advantage of just being able to do it reasonably quickly, simply because I do it all the time.
Sure.
But
that makes a huge difference, doesn't it? For those who don't realize, it's it makes a massive difference.
Yeah. And I honestly don't think you can really, really learn electronics without learning how to test. It's such a huge part of it. I mean, there's the things you pick up when you build something. It doesn't even compare to the additional experience you get by doing that from just looking at it from the theoretical perspective. And not that the theory is not valuable. They have to go hand in hand, which is why I spend a lot of my videos. I say, look, here's the theory, here's the calculation, and here's the circuit, and here's the measurement. This is how you measure it. This is how you design it. And this whole picture is the whole experience. And I hope people do spend the time to try and build it.
Yeah, because the theory without the there's some phrase about that too, where it's like theory without practice is something, I don't know, but but I mean, basically, I think about my days of like starting on electronics and not having the theory and just kind of like trying this, pushing this wire here, trying this, trying that, and that causes just as much as confusion as never trying it at all, and going through a simulator and being like, oh well, the answer is a gigaamp. That
gigaamp. I'd like to see what problem you've solved where a gigaamp was the answer.
Yeah, well, Splice was not always my friend.
I was actually listening to what Dave was talking about recently when he was talking about what qualifies as a hobbyist and what skills you should have as a hobbyist.
Right. Yeah.
And I know people are discussing and giving sometimes Dave a hard time, or you're being too tough on. But the thing is, my perspective is, you have to have those skills. I mean, you need those skills. First of all, you need those skills to distinguish yourself. If everybody is going to, if everyone's going to be able to, everyone's going to play with an Arduino, how are you going to be the person who does more? You have to know more. There's no question about it. And the second thing is that, I mean, I like the fact that Arduino has made so many things, available to people, and people can build all these complicated and wonderful things. This is great. My only fear and my only concern with this Arduino ecosystem is that sometimes it can give people the wrong impression that they have accomplished something. But in reality, they haven't. Even though the outcome is very impressive, but that's not. They didn't do that. The outcome is just a part of the ecosystem they became a part of. That's not what they did. And it's very easy to tell. Just wire up your microcontroller once. Just do it yourself. Yep. Just put it on a breadboard. Put your crystal. Put your decoupling. And just find out how many problems you're going to run into. and you'll see the difference then.
It's exactly like building up a kit and it works first go.
Yeah.
What have you learned?
Yeah,
Well, you've learned
exactly.
how to build a kit. You've learned, like apart from that, you've learned nothing.
Yes. No, it's not
Like,
that. I mean, the experience is rewarding, and there's definitely learning.
Of course.
But yeah, I mean, if you want to really, that you have to be careful to distinguish what should make us feel satisfied at the end of a project. What is that sense of what exactly have you gotten out of it? And that's why I mentioned this one of the videos before, based essentially in agreement with what you were saying, is that I have learned so much from messing things up and things not working.
Yeah.
Make things that don't work,
Totally.
so you can learn something from it. Yeah. So that's my only goal. You know, to make an LED blink on a microcontroller was a colossal undertaking 20 years ago for me.
That's right. I know.
So now it's just you just plug it in and it's there. It's great. I think it's the fact that it's so available and then so many people are using it and there's so many amazing things people do with it is wonderful. I would never take anything away from that. I just want to make sure that people don't underestimate and eliminate that foundation that is needed to really feel like you've done something.
So what I'm hearing here is that you need to jump into analog to really feel accomplished. Is that what I'm really hearing here?
No. It doesn't have to be analog. You have to build a couple of things from scratch. If you have an Arduino setup, I should be able to come and ask you 10 questions about exactly how something works, and you should be able to know those answers, and you should ask yourself those questions, and that would be great, and I hope that people continue to do that.
We've always said here on the Amp Hour that I think we're pretty much in agreement here that we don't care how people get into the hobby or get into the field, as long as they do.
Yes.
So that's the beauty of the whole hacker maker, / Arduino thing, is that there's so many more people actually getting in there. And playing.
Yeah, I mean, this was inconceivable before.
Yeah, I know it's not the ideal way that we'd like it to happen, but the fact that it's happening is, brilliant.
Yeah, absolutely. I really, really am amazed of what has happened with this Arduino ecosystem and the things that you can do that, I mean, it was completely impossible before. It is amazing. I appreciate the whole thing.
And it's nothing actually to do with the Arduino hardware or software itself.
No.
It's just the ecosystem which is and the community which is built up around it.
Yep, exactly.
I mean, it's just absolutely remarkable.
Yeah.
I mean, this hardware and software ecosystem has been there for 20 plus years,
absolutely.
30 years. I mean, there's been these development boards and easy to use, development environments around for a long time. But for some reason, it's just sort of boom, it's exploded.
Yeah, absolutely.
It's great.
It is. It's definitely no complaint from me.
So you mentioned that you're really big on the education, especially that kind of reaching into, helping people that are less privileged in terms of like background and stuff like that. Have you had any experiences with that where you've heard from users that have been like, because of your videos, I'm now working on millimeter wave craziness like you are, that kind of thing?
I certainly have had a lot of wonderful and encouraging and kind comments from many of the viewers, expressing not just simply their gratitude, but also expressing the fact that I have sparked their interest, given them this sense of curiosity, this sense of understanding, and they now, in one way or another, in a small way perhaps, equate this sense of understanding with the joy they get from doing something. And that spark, I think, is far, far more valuable than any specific lesson that I can give anyone. I have people who have done this for me in my past. My uncle, for example, my uncles, both of them are brilliant men. And they taught me so much. They gave me this sense of curiosity. I remember one of my earlier memories was, I don't remember even how old I was, might have been 6 or 7. My uncle told me that, remember that if a day passes where you learned nothing new, is a day where you have been dead.
I like that.
That you haven't lived, you haven't been alive in that day. I mean, that is a really, really powerful message, and it's to follow and take that to heart. And I think can be, and I'm in his debt for giving me that perspective. It's all about perspectives, how you look at the world and how you look at everything that happens around you. And this is a very beautiful lesson to be able to teach somebody. especially at a young age.
Yeah, it's a very interesting point you raised there, because I see the same thing. Like, I don't see the actual video. Like, I might do a whiteboard tutorial on op amps or something, right? And it's not necessarily that I'm teaching people that particular thing, right? It's that I'm encouraging them to be interested in it. And so that's why I don't necessarily, care what style of video I do, as long as I keep it interesting and entertaining and enthusiastic. That's what, and people have said that. That's what they've said. Oh, it wasn't one video. It's just your attitude that got me back into it.
Yes.
I was a hobbyist 30 years ago and I gave it up, and now you've sparked my interest again. And, there's countless people who have said that. It's not the specific video. And I think you've seen the same thing. It's not, a specific thing that you're actually teaching them. It's more of a general, getting people interested.
Yes. I mean, it's in your voice. It's in your mannerism. I mean, passion exudes itself. You can detect it as soon as somebody is passionate about something. It really, and it really shows, and it's a wonderful thing.
So that's why I consider myself more of an entertainer than than an educator. As such,
I mean, you do that too.
People might learn, stuff on the side by watching my videos, but that's not the whole intent of my videos. Is not to, just teach, everything. It's just, give people something they can watch that's better than some soap opera, perhaps.
Yeah, I mean, it's quite compared to, obviously, your work, you have so many episodes, I must be almost 700 by now, if I'm not mistaken.
Pretty darn close.
So I have only 40-something episodes, so it's not even close. It's an order of magnitude off already. So, but
it doesn't matter. It's the fact that you have the same type of enthusiasm, and yours are highly technical, educational content compared to mine. I mean, there's quite a big difference there between your educational ones and my attempted educational ones, purely from your background. And
I have to say that the cryogenic stuff was one of my favorite of yours. That was
right. Yep.
Stuff that I just never even knew about after,
Oh, that's great.
Undergraduate degrees.
Yeah, that's cool.
Very
that's
cool.
cool. Yeah, I have. I mean, I do want to do. Sometimes I do want to do more things related to physics as well, because it is something that I am interested in. And sometimes I dive a little bit into things that are a little different than electronics, like when I did the monochrometer experiments, or when I talk about wavelength meters and things like that. Those are free space optics stuff. Is pretty interesting. It's not my expertise, but it is something that I've always enjoyed, and I definitely like making those videos. And of course, I like playing with test gear. I mean, who doesn't like to play with test gear?
Yeah, exactly. I know.
So
we can be accused of being test gear freaks.
Oh my god! Absolutely. And I mean, at work, I have basically the state of the art of anything that you can imagine at work. So I'm surrounded by wonderful test gear all the time.
How much custom test gear do you have to build? I can imagine you're building custom jigs and interfaces and front ends, perhaps. Do you have to build any complex test gear yourself?
Yeah, I mean, some things has to be complex and custom. For example, just give you a simple example there. Let's say you want to generate a signal at 100 gigahertz to test an amplifier that you have at 100 gigahertz, right? And then you want to measure its linearity. You want to measure how linear is this amplifier at 100 gigahertz. Now, if you want to measure how linear something is at 1 gigahertz, it's fairly straightforward. But at 100 gigahertz, you're going to have to generate two tones of signal that are, separated by a certain frequency, so that you can do intermodulation product tests and things like that. Generating two tones next to each other at 100 gigahertz, well, not so easy. So you'll have to kind of, you have to put together a bunch of microwave components to be able to combine different signals, and then put attenuators and so on and combine them and then get two tones. And nowadays, of course, more and more equipment is available at 100 gigahertz up to 5 terahertz even of test equipment is reasonably possible to do. And they all operate on the same principle, basically. I mean, network analyzers up to several terahertz are now pretty easy to make nowadays. More complex.
Really?
Yeah, because they all operate on the same principle of operation. They all have
Right,
Yeah,
of course.
they all use signal
it.
multiplication, and they all use detectors and so on. And so they're easy to buy. When I say easy, I mean they're very expensive, but they're well
But they
understood.
take your money quickly, huh?
Yeah. So they're people make them all the time. There are several manufacturers that do it. And yeah, go ahead.
Who's this?
I mean, VDA, Virginia Diode makes them. OML makes them. Agilent or Keysight, which rebrands, I believe, other people's extenders. Because for a company like VDI, Virginia Diodes, that makes extenders up to a couple of terahertz or so, they don't make network analyzers themselves. That doesn't make any sense. So they make extenders which attach to network analyzers. Then the whole system can then now measure S parameters in a particular band. Let's say 110 to 170 or 270 to 400 and so on. So then they make those extenders for Keysight or for Anritsu and so on and on. And so they do it. So now we can do that fairly easy. But sometimes some tests will be more difficult. Now I would say making tests. When I was a student, making tests at 110 gigahertz it was pretty tough. Nowadays, making tests at 500 gigahertz would be equivalent. It just keeps moving.
Kids these days, right?
Kids these days. And the terahertz transmitters, yeah.
Yeah, seriously.
In their mum's basement.
Yeah. So nowadays you can do these kind of, and people underestimate. I mean, generating a signal at 100 gigahertz is tough for sure, but I think even from eBay you might be able to pick up some stuff to ultimately generate 100 gigahertz.
Yeah, probably.
But the thing is that because of in the United States it might be a little bit easier, but other countries it's very tough because there are very strict regulations on how much power you can be able to generate and transmit at above 90 gigahertz or so because of military restrictions.
Yeah, ITAR.
Yeah, ITAR limitation.
Just remember, kids, it's only illegal if you get caught, okay? Just remember.
Yeah, if you
And
can
as an American, I
generate,
can say Dave does not speak for me. As someone who's easy to get to, Dave does not speak for me.
yes. And this is one of the things that I have, strictly tried to adhere to is that everything that I do on the signal path is 100% separated from everything that I do from professionally. The signal path stuff is completely isolated. All my test gear is completely separate. All my own test gear, nothing to do with Bell Labs at all. So, that way that there's a good distinction, which is very important.
Okay, so you would, even if you were allowed to, you wouldn't feel right using Bell Labs test key.
Oh yeah, for sure. I mean, there's complete separation from that perspective. Even when, for example, I did a tutorial and demonstration of the Keysight's or Agilent's 62 gigahertz oscilloscope, which
I assume that you got that from Bell Labs.
No, that's directly loaned to me from Agilent. That's not from Bell Labs. Yeah. No, I would not. I would not take that from. I wouldn't take that out of the building. That's a $500,000 equipment.
Yeah.
Oops, I dropped it.
So it's every time. Even if you ever see gear that is really really high end, is directly loaned to me by the manufacturer. It's never from Bell Labs.
But you've got the contacts in them to go, hey,
Yeah, they know me, and they've seen videos, and obviously they know the kind of work that I do, so they don't mind loaning it to me for a really really high end gear. Obviously, I can't hold on to it for 3 months, but I can hold on to it for a couple of days because even just to rent a 62 gigahertz $500,000 scope for a week, it will cost you. $10,000. So
holy crap.
I know, totally.
So
at minimum.
at least.
And some people have asked me, why don't I get a scope like that here in the lab? I'm going, well, there's probably not even one in this country. These things aren't just left lying around the the demo showroom floor.
No. I mean, it's a very very
scopes.
specific, extremely specific application. There's really very few places where you would need a 62 gigahertz or 100 gigahertz oscilloscope. I mean, the only reason you would ever pick up a 100 gigahertz oscilloscope is because you're doing state-of-the-art optoelectronic experiments.
Yeah. And they wouldn't even keep it in stock. You order one and they'll build it for you.
Yeah, absolutely.
I think that's how it works.
And that's another example of, for example, somewhere where 3.5 technologies come into play. So the 62 gigahertz scope from Keysight, it has a front end which they call Real Edge, which is their their own frequency stitching stuff, which they talk about in the datasheet of the instrument. That's a 3.5 technology component.
Yeah.
Right. So
Got it.
they make 100 of them, and then they measure them, and maybe one or two of them will fit what they're looking for.
Right, interesting. Yeah, that's why these things cost. Yeah, that's why they cost $500,000.
Because you don't need to make them for volume. You make one or two, every couple of months maybe, and then these things take. I mean, the calibration, the factory calibration of that scope must be, maybe 10 hours.
I know.
It must be insane.
Yep.
Yeah.
Wow. Do you think that that'll change in the future? So, I see all these scope makers, they're all moving up market in terms of, everybody's going to higher frequency stuff. But, do you think that as someone working on millimeter wave stuff, is the general technology moving all that way too? I mean, are there going to be necessary for more... is it just going to continue to spread, or will the bulk of people keep moving up in frequency to need those kind of higher end scopes?
Well, so the scope is an interesting thing because you are fighting physics at some point. There is an issue of ultimately running into a jitter noise floor of a sampling system. I mean, there is a very simple equation that relates jitter of a clock of a converter to the maximum effective number of bits you can ever achieve. I mean, if you don't have the jitter, you don't have the bits. It's end of story. And it's almost like the Shannon's limit. You have to create. You have to be able to create, or you have to be able to de-embed that jitter somehow by having some correlated source and so on. It's very complex. Right. So you will run into some floor. This rapid move that you see in scope performance is happening because ASICs around 5 or 6 or 10 gigasample per second are becoming more and more common, especially in CMOS, because you can make very sophisticated, dense calibration algorithms and mechanism in a CMOS process, and then you can make ADCs using that. But once you're talking about, 160 gigasample per second or 240 gigasample per second, like Teledyne LaCroix stuff. Those are really, really, really specialized. But anyhow, once you hit 110 gigahertz bandwidth, then you are out of connectors type. You are at a 1 millimeter connector, and that's that. The only way you can go higher, you can maybe go to 140 gigahertz by using that proprietary Anritsu 0.8 millimeter connector, which is supposed to have 180 gigahertz coaxial bandwidth. But then let's put that aside. At 110 gigahertz, your connector, 1 millimeter connector, is no longer 50 ohms. You hit the mode of the connector. So you hit the mode of the connector. So now you don't have DC to 110 anymore. Yeah, you can start digitizing things in bands of frequency. Now you would go from 110 to 170, which is a D band. But the question is why don't you just find a way to down convert that back onto the So it really I don't see. I'm sure they'll find. I'm sure something will come up. If I could digitize 110 gigahertz or 200 gigahertz straight up by an A to D converter, I mean that's insane, right? What we're saying is that you can connect even with the Agilent 62 gigahertz scope. What are we really saying? We're saying that you can take a horn antenna or an antenna and connect directly to the scope input, and then you can receive 60 gigahertz radio straight up with nothing else, right? That's just crazy. If you think about it, 10 years ago, people would have laughed at you. Right?
I know.
Right. But that's what I'm thinking, though. Like maybe in 10 years we'll listen to this and be laughing. I mean, obviously there's some limits there, but maybe there's other things, right?
Again, because some physics are at play here. So yes, you're right. It will get better. It will get cheaper. That's one thing, right? It will become more accessible, more available, and perhaps higher and higher at some point. But there is going to be, again, this is also driven by finance too, right? There has to be somebody who needs it. That will make sense. Remember, these scopes, the 100 gigahertz scopes or so on, they're intended for optoelectronic, for broadband application, where you need to receive DC to 110 at the same time because you have a fiber channel that supports that kind of data rate and so on. That's really one of the main reasons why they're making these things. And if you look at Bell Labs regularly publishes papers with the state-of-the-art oscilloscope. Every time a new oscilloscope comes out, Bell Labs has a new paper showing a next highest ever achieved data rate through fiber. Why? Because now they can receive it. Before they couldn't receive it. That's really the limitation, because transmitting is a lot easier than receiving.
Right. You can be throwing garbage to the universe. You just don't know what you're doing.
So to generate 100 gigabit per second is very, very different than to receive 100 gigabit per second. It's a very different problem. So as a result of that, that's why every time a new scope comes out, there's new publications in that field, is because people can now actually do it. But whether it's going to go above that, the connector is an issue, the market is an issue, the physics is a problem. But even even now, I have to admit, thinking that 100, 200 gigasample per second was going to happen so quickly, I was skeptical. Yeah, especially because I built millimeter wave data converters when I was a student. That was my thesis. So I appreciate the remarkable complexity and the extremely impressive accomplishment that's gone into it.
If you're talking general purpose scopes, then they're always going to be limited to 500 or 1 gig. Why? It's the probing solutions, right? Passive probes that people are so used to, like, 500. You can get ones that go to a gig in a passive scope, but then, it's just, just for your average general use, even if the technology's there, they're still going to be limited to like 500 or 1 gig.
Just because you need to get like sub 10 picofarad kind of probes in and stuff and crazy.
Well, you've got to go to your active probes or your handmade probes, right? Your custom made probes for your, So and people don't want to do that. People just want to use their general purpose scope. So, it doesn't matter how good the data converters get and everything else. Okay, you might be able to have a 2 or 3 gigahertz bandwidth front end scope, but what's the point for general use unless you've got the unless you're able to probe signals with it.
Yeah, that's basically your limitation, and but the way people tend to sometimes get around that issue is by creating scopes where they say, up to a gigahertz or up to 500 megahertz or so, you're a passive probe. But if you want to go more than that, we're going to switch to 50 ohm. Yeah. And now you cannot use connected active passive probe, and you need an active probe. But there's only so much you can do. Again, that's this physics is time constant. There's nothing you can do about it. You're stuck.
No, exactly.
You're stuck at 500 megahertz. So it doesn't matter how fast the technology changes. It's a matter of physics.
But I think we're already seeing that scopes, they actually design the front ends for 500 meg and they sell them as 100 meg software limited bandwidth scope. It's like we're already seeing that.
Yeah, I mean, all the Agilent Keysight is famous for that. They built their scopes. Exactly. Essentially, there's only one hardware they sell, and they sell keys, license keys that can cost $50, $100, $200, even $1,000 to unlock a feature that's already there in hardware.
Because it pays them to do that. Like within the last 10 years, we've seen a shift from it was difficult and expensive to roll a 500 megahertz front end to actually manufacture one. Now it's like anyone can buy chips from anyone can almost go out and design their own 500 megahertz front end scope.
Yeah,
right?
I mean, because exactly
using just chips you can buy from Mouser and DigiKey, right? It's
nowadays
it's not that hard.
Yeah, exactly, and it makes sense for them to have one type of hardware. Is cheaper to develop, cheaper to produce. To have one part number, one bill of material, one design, one PCB, and then they just do that, and then they just say, we may sell, let's say, the 1 gigahertz model at a 5% loss or break even, but when we sell the 8 gigahertz one, we'll make enough to compensate for the whole thing, and the whole project has profit. That's kind of how it works out at the end of the day.
And it means the smaller players, Rigol and those that are up and coming, they can design. The chips are out there because they don't roll their own custom silicon. They're just using off-the-shelf devices like anyone else could. I mean, anyone in theory can come along and design a Rigol level 500 megahertz scope, for example.
Yeah, it's all off the shelf.
All the parts are out there. Yeah, it's all off the shelf.
Well, we were talking a little before the show about that too, right? I mean, Shari already said that you liked how that's kind of opening up the market too, and kind of accessibility stuff like that.
Yeah, I mean, it's always good to have manufacturers like Rigol or Siglent or other people in the same ecosystem space to do that, because it does two things. It makes cheaper instruments available, and it gives the higher guys a run for their money. Now they have to either drop their prices or do something to stay competitive in that space, right? And this is of course, as long as manufacturers are fighting each other, it's good for the consumers. It's a known fact. So let them fight. It's a good thing. It's a good thing.
Yeah.
Even 5 years ago, it's unheard of, the scopes that you can get these days for the price that you couldn't get 5 years ago, let alone 10 years ago, And in the scheme of things, that's not a long time.
I know. I was cleaning up the lab the other day at work, and I was just throwing away all these old scopes, the CRT scopes. I was like, oh my God, these things must have cost a fortune at the time. Remember those gigantic Tektronix mainframes, those huge ones with a lot of
the 5,000 and 7,000
but
series.
they had to throw those away and recycle them and so on. I'm like, wow, these things must have cost a fortune. Now
that they would go dump some that in there.
They're too old actually, even for they're enormous. I mean, this thing is like the size of a stove. Where are you going to put that? So
heat your house.
Yeah, it would heat your house too, because it's just that thing must burn so much power.
Yeah. Nice and
linear. Goodness.
Right? yeah, nice and linear. Yeah.
We were talking also before the show about your publications, which we'll link in.
Mm-hmm. Yeah.
But you can only read the abstracts. And you were saying before the show that you don't hold the copyright on these anymore. You effectively give that to the IEEE.
Yeah.
Can you tell us how that works, how you're affiliated with the IEEE and how they get your content?
Well, of course, I'm an IEEE member myself, and IEEE Solid State Society member and so on. IEEE is a non-for-profit organization, as far as I know. I hope I'm correct about that. They're non-for-profit.
I think you are.
But that doesn't mean they're non-for-profit. Doesn't mean they're non-profit. They still probably make money.
There's a difference.
They do.
They have to stay viable.
Yes,
they've got to remain
viable. They employ a lot of people.
That means they have to make a profit.
And they employ a ton of people. Yeah. And every time there's a conference, various conferences that I attend, like the ISSCC, which is the biggest one in my field, or CISIX, where I'm the chair of one of the millimeter wave and terahertz sessions, or RFIC, and so on. These conferences all associated with. Connected to IEEE. So they live in the ecosystem of IEEE in one way or another. So because IEEE is essentially responsible for distributing journals and publications, contents, once you publish something with IEEE and then have it show up on their system and then take care of everything, you give the copyright of the paper to them. You're giving obviously the work is yours, and you're not giving away the work, just a publication, the paper itself. That the right of that is there. So I believe that if I were to put my own papers on somewhere where people can download the whole content, I believe I'd be violating some IEEE regulation, if I'm not mistaken. I don't think I can just do that. Yeah, so you have to be an IEEE member. But if you're not an IEEE member, if you're a student, you have to be an IEEE member. First of all, it's really cheap for students. And exactly. it shows up once you graduate, how many years you've been an IEEE member. And that's an important thing. If somebody comes along and they're trying to hire you and they look at your resume and they say, well, this guy's been an IEEE member for 10 years, and he's just coming out of university. That's good. That's impressive. It means that right when you started your undergraduate degree, you already had a vision of what this whole ecosystem was about.
Yep. I lost that because I used to be a student member way, 20 years ago.
Way back,
in the day. Yeah, way back. And then, I just didn't bother. And then I only joined again the IEEE 7 years ago or something.
Yes.
So my little card says, you're only a 7-year member,
Yeah, it's okay. I mean, that doesn't, it's still 7 years, it's still quite a long time. I think 10 years, depending on, I think, the publications and so on, you have to be an active researcher, but then you can become a senior member and so on. And then there's also IEEE Fellows, which is a whole different story, becoming one of those. Yep. But I mean, it's and depending on which magazines and so on you subscribe to, it's a different price. It can be pretty expensive. I think I paid something like $250 a year or something to be a member.
Yeah, your basic subscription to IEEE without any of the optional mags. Like what's the correct term?
The journal papers. Journals. Yeah.
Journals. Right. Yeah, you can join. They've got like 50 different journals you can sign up to. Yeah, the basic price is like 120 or 150 a year or something.
Yeah, it's it's still not that bad, less than $10 a month.
Right, so is there any other place you would publish anything?
Besides IEEE?
Are there any other journals? Yeah.
No, I don't think so. I mean, you normally, typically in my field at least, the way it works is that we generally publish something at a conference. And if the paper is well received and it's good technical content, then it gets typically invited for a journal publication. That can either be a journal publication at the solid state circuit.
So it's a two-step thing.
Yeah, usually.
So you can't go straight to journal?
No, you can. You can submit your work directly to the journal. Sometimes it's advantageous to be invited because the review process for a journal, when it's invited, is typically a little bit shorter because there's a deadline for where the special issue of the journal comes out for that particular publication, for the particular conference. So it's a little bit faster. But because this is a very involved review process, you submit it and it's heavily peer reviewed. It gets sent to, several experts. They read your paper and they grill you on it and they send you all their questions.
Really? Okay. Yeah. So, but what I've always wondered about is, what if you are the expert on it? Who is going to peer review you? If you're at the bleeding edge, who is going to?
It's almost impossible to be the only person that has an expert at a particular topic. But even if you're not an expert,
but how many people have they got willing to be peer?
Oh, they ask. Usually what they do is they ask people who are famous in that research, or they ask people who are referenced in the paper. I have done many paper reviews myself. Yeah, so I get requests from the editor of the particular journal if I want to review it, and then they have a timeline to review it, and then I have to write all the questions and so on. Obviously, the person who wrote the paper doesn't know who I am. They don't know who the reviewers are.
Of course,
it's not double blind. It's only half blind, I guess. Yeah.
So is this a paid thing? Do they pay you to review the paper, or is it just you do it because you're part of the society?
Yeah, you do it because you're part of the ecosystem. Yeah, no, it's not paid at all.
Right.
Yeah. And the reviews take quite a long time too. It's not something you do in 10 minutes. It's hours and hours because you really have to understand what the person has done and look into it because this is a scientific endeavor essentially. You want to make sure that the science is correct. That's the whole point of the peer review. So you have to be very critical and be very careful about what's out there and what people are saying. And
if you've got questions, do you funnel it back through the IEEE and remain totally anonymous, or would you contact the author? And
no, you don't contact them.
Say I'm a reviewer.
No, you don't, because the author is never supposed to know who the reviewer is. But you type your questions and you submit it to the.
There's an online thing.
The editor basically takes care of it. The editor of the journal. Got it. Yeah, he or she will take care of it.
And they would be full-time employees, the journal editors, I would assume. It'd be a lot of work.
Well, the editors rotate around. They're not employees. Typically, they're professors or professionals and so on. I've never been an editor myself. It's actually quite a lot of work, too, if you are...
I was going to say, I'm assuming that'd be a paid position somehow.
I don't know. I wonder.
Or is your university expected to allow you time? It's like, you have to go to jury duty. Okay, you've got to go to... You've got to spend some time peer reviewing or being an editor.
I'm pretty sure that professors at universities are granted and in fact encouraged to be. I mean, to be an editor of, let's say, Journal of Solid State circuits for a particular issue is an honor.
Yeah. Yes. Yeah. Totally.
That's quite an accomplishment.
Another feather in their cap as well.
Yeah,
right?
absolutely.
I don't know. How do you feel about the whole publishing? I mean, because I read a lot about. Obviously, I've never done it, so that's my big, disclaimer.
Same here.
But how do you feel about the whole process? I mean, maybe it's different with this kind of stuff, but some of it seems like the publisher parish kind of model seems like it's kind of constrained and forced. Has it worked out well for you, or what's your take?
Well, for me, in terms of my performance from my work, obviously publications are a good thing, but sometimes the model for the company changes a little bit and there's more product development in mind, and as soon as things become product development, then you're not really allowed to publish. I have a lot of work right now that unfortunately I cannot publish because they're secret or they are product oriented and we don't want to give away the secrets in a way, right? So then I can't publish, even though I really like the idea of publishing. I like the idea of being involved in that. So I have been unfortunately a little bit out of the picture in the last couple of years because of that. But hopefully I'll have some new stuff coming up later. But in terms of one of the things that I sometimes don't like is that sometimes because having many publications tends to be important, people break up a work into many papers. Even though it's supposed to really be just one paper, like that phased array.
I can get 5 out of this.
Yeah, and that's sometimes it works like that. Like my other work, the phased array chipset. Yeah, I probably could have written 3 or 4 papers with it, but we just wrote one because, and I think that people do recognize that, they pick up a paper and say, wow, this is a complete system. And there's just one paper is everything and it works, right? That's impressive that people do pay attention to that. But it's sometimes, occasionally, they can become a games number, a numbers game. So then, it's like, you have 300 publications or 200 publications. And there are, by the way, people in my field with that many publications where each publication is something important. So don't get me wrong. That, there is no shortage of brilliant researchers in my field. That's for sure. And that's definitely possible. But sometimes people break it up.
Is there? You mentioned like sometimes the pressure from, say, Bell Labs, for example, for keeping things secret because this is going to be a commercial thing or whatever. Is there a temptation for a company like Bell Labs to sort of fall into the trap of, well, everything is secret and then not publish damn well anything because they get so paranoid that, this could make us a buttload of money, so we won't publish it?
Yeah, I mean, they have to strike a balance between being to maintain their presence in research and generating ideas where they are in the system all the time, where they are at the top of the page, and creating a situation where you are developing products where end up being something very valuable for the company. Sometimes papers from the industry tend to read like data sheet, which is kind of annoying. Where it's just like here's what we got. I'm like, that's great, but how did you do that? That's what.
How did you do it?
That's the sauce, man.
Yeah, that's what I wanted. That's what I wanted to see. So sometimes, and I understand why they do that. It's not like the person who wrote the paper necessarily says, I'm not going to share this. It's because they can't. And sometimes even when I write papers, sometimes I have to hold back some detail because I won't. Otherwise it won't be released. Otherwise, the people in the company who look at it, it's like, oh no, this is too much detail, right? And
and that I was going to say, the cynical side of me says, well, that means that always only the dregs are going to get published. All the really cool shit is going to be kept secret.
I don't think so, Dave. We've seen. We're looking at a list of his papers here. These are amazing.
Yeah. But I reckon there's some ultra cool stuff beyond that he's not releasing.
Yeah, I mean, compared to some of the other people doing millimeter wave, especially people in university, my publications is tiny. There's some my supervisors, my professors from the University of California, UCSC, and other people. They have a long list of incredible. Their students obviously do the work, but they're the supervising entity. They're the leader.
So their name gets up in lines.
And they are of course driving the ideas and constantly monitoring and supporting and generating ideas with the students too. And they have tons of really amazing, impressive work. It's no shortage of. There's a really good. Even though I say that there are all these amazing people out there, there's Christopher Hitchens once said something that I think is brilliant. He said that even though I have met many, many people much smarter and more intelligent than myself, I have never met somebody who can say differently. And I think that's brilliant. Just essentially saying that, there's always brilliant people out there, but no one's ever brilliant enough to not say that statement itself. That's
right.
Yeah, it's pretty nice way of putting it. But there's lots of great people whom I learn from continuously. And that's one of the reasons of being part of the IEEE is so important, because you stay up to date with the latest publications and ideas.
Right.
You don't reinvent the wheel. Otherwise, you end up reinventing the wheel.
Do you ever see people that are going to the so did you say is it the ice cream conference? Is that the one that you go to? The ICSS or whatever it is?
Yeah, I go.
Ice cream.
Yeah, I go to a couple of conferences. The ISSCC. That's one of them, the International Conference of Circuits and Systems Societies. Circuits and Systems.
Yeah, isn't that called ice cream sometimes? Isn't people call that? No?
I don't know. I don't think anyone's ever called it that I know. But I'm going to start calling it that.
Well, there's some kind of acronym that looks like that someone called it the ice cream conference. So I don't. That's why I called it that.
I don't know, but from now on, I'm gonna. That's what I'm gonna call it. There's that.
Awesome.
There's the RFIC, which is a radio frequency integrated circuits. There's SysX, compound semiconductor circuits and systems, and so on. Those are the main ones that I attend, which are all circuits conferences. And then there's conferences that cover more systems, and then there is conferences that cover optics and so on.
So how many people would turn up to these? How big are these conferences?
Well, some of them are something like the IMS conference. The IMS RFIC combination has several thousands, 5,000 maybe.
Oh,
yeah.
Wow.
Some other conferences are much smaller,
huge.
like RFIC and SysX, for example. SysX would be maybe about 250 people. Yeah, depends. ISSs is pretty
Right.
big, several thousand also, 4 or 5,000 also.
Now, would people actually rock up and show off their hardware? Hey, check this out, mate. Whip it out on the bench, or is it just death by PowerPoint?
No, there is definitely some hardware sometimes being demonstrated, but because these are all circuit conferences and they're all ASICs, there's really not much to show
right,
sometimes,
yeah,
right?
right.
But yeah, there is
Got it.
at IMS conference there is an enormous industry show, which I think you would absolutely love because all this state-of-the-art instrument from every manufacturer is there.
Yeah.
Yeah,
Yep.
that's
Yep.
pretty awesome.
Test equipment.
Oh my
pool.
god, yeah.
Yep.
I mean, you can spend 4 or 5 days just doing that.
That's awesome.
Wow. Fantastic.
But can we hear a little bit more about some of your papers here too? Because so you've shown some of these off at the conferences and stuff, but what are some of these used for as well? So we talked a little before the show about the phased array, and I mentioned that Greg Charvat, who we've had on the show, does some phased array stuff too. Mm-hmm. But what is all this stuff?
Well, like I said, I've done different things for different applications. I mentioned, let's say the 160 gigahertz PLL that I did a while back when I was a student. That was for potentially used for something like a medical imaging system, where at 160 gigahertz, some interesting properties come to play, where you can image tissue material, and you can find hidden weaponry and things like that by using millimeter wave imagers, which I'm sure you've seen at airports and so on. So that's that kind of application. Then there is the phased array stuff is interesting because essentially the idea of a phased array is a system where you can steer a beam, a pattern, by combining it in the air at a particular way. So it's basically constructive destructive interference. And you can have an array, a grid of antennas, for example, and by spacing them and delaying the signal that gets into each of the elements appropriately, you can create constructive destructive interferences in a particular way that you want, and you can actually have the beam to point in a certain direction, even though the antenna itself is not pointing in that direction.
Yes.
So why is that? Why would that be useful? But there's many different reasons why. But let's say you make a phased array system of a mobile device, and you're moving around, and you want the beam to track you so that you always have signal strength no matter where you go. Because at some of these higher frequencies, the attenuation and the signal losses are so large that you have to always be pointing to the person. Otherwise, there's no signal. There's no nothing to detect. So that there you can use, for example, a phased array when a moving target is involved.
And this works anywhere from ultrasonics, and I've done this at around about 1 meg, which is an underwater steered beam sonar system.
Absolutely.
And you can do this up in the hundreds of gigs.
This is a wave.
If you want
this is
as
a
well.
wave property, so it will work at any frequency. The reason I work at 90 gigahertz for the phased array, where the carrier frequency, the RF carrier frequency of the signal is at 90 gigahertz. That's 90. The reason is because at 90 gigahertz, your relative bandwidth that's available to you to occupy the signal is much larger than it would be at 2.4 gigahertz. Right? In 2.4 gigahertz, you're crowded with channels of different types of communications. At 90 gigahertz is essentially quiet. There's nobody there. So
why 90? Why not 80 or 70 or 50?
all of those have applications. So 71 to 76, 81 to 86, for example, is a band called the E band, and it's a recently opened band, reasonably recently opened band, where you can do telecommunication at that band. The 60 gigahertz is an available, reasonably hot topic, and there've been products in there too. 60 gigahertz is interesting because 60 gigahertz starts interacting with water molecules in the air. So the loss is very high. So 60 gigahertz is good for short range. If you want to flood an environment with a whole bunch of different people communicating at 60 gigahertz, you can without them interfering with each other too much because the loss is so high. So people build systems there.
So very, very, very short range. We're talking meters
exactly. I mean, not that people do build 60 gigahertz systems for long range with very high gain antennas too, but the loss is quite high. Right. So that's the advantage. So at 90 gigahertz is another interesting frequency because again it's open. Its losses are actually quite low at that frequency compared to 60 gigahertz, and you can do a lot of bandwidth. You have a lot of bandwidth. It's free space. It's a military likes to use that because it's secure and so on, and that's the kind of reason why we went. But the paper targets really, really high bandwidth wireless system. So where we send 10 gigabit per second through the air, using a phased array, at 90 gigahertz, is just to demonstrate, look, you can do this. And this is with a complex constellation. This is a QAM, 16 QAM or 32 QAM constellation. So it's reasonably spectrally efficient. And that's kind of targeted for that. So that's all wireless stuff. And then other things that I've done in the past that might be interesting is things like retimers and receivers for optoelectronic industry, is that when you want to send data through a fiber channel, for example, you could use just digital ones and zeros, right? The very basic 1-0 serial data. So you can imagine what goes through USB, which is a differential serial data. Imagine that now going through light, through a fiber. And then you can put a crazy amount of data through fiber because the optical bandwidth of fiber is so huge.
How huge is it for those who...
It would be easily hundreds of gigahertz. But it depends on how far you go, because if you go really, really far, just like anything, you get dispersion. These wavelengths start to separate from each other.
That's right.
So you run into other problems. But compared to a copper wire, fiber is almost lossless.
So fiber is still the best medium over copper, air, wet string, anything. Fiber is still the best.
No, but now I'm tempted to go and measure the S parameters of a wet string that you mentioned.
String, I know. You've got to do a whole paper on it for the April edition. For the April edition of the journal.
Yeah, that would put me on the map. So
definitely.
Fiber is definitely, it would be the lowest loss. It's certainly by far. I mean, you can go, obviously thousands of kilometers.
Lowest loss and widest bandwidth.
Yeah, it is. It is it's the lowest loss widest, but especially because fiber is not
for a given.
I mean, fiber is not line of sight, so it's even more advantageous when we put it under the ocean, right? I mean, it goes 3,000 kilometers.
That's right.
Not that those systems are not.
That's how we're talking to Dave
complicated.
Right now.
Yeah, exactly.
Yeah, but they have repeaters. Like it's not a single fiber that goes 3,000 kilometers, right? They have repeaters every 10Ks or something.
Yeah, they have to. They have optical amplifiers, EDFAs in the way. They have repeaters where they go back to electrical. They do equalization. They do error correction, and they retransmit. They have to do those things if they want to make it, in those long distances. They're long haul links.
How do they get the power down there? Because I've worked on 10 kilometer towed array systems, and just getting the power down to all the modules right at the, I've actually modeled, the transmission line, like the actual the power transmission line system, and it's just for 10 kilometers is complex. I can't imagine 3,000 kilometers.
I mean, they send the power with the fiber, right? The cable that they put, in some of the instances that I know, is the cable they put under the ocean is not just a tiny single fiber. Obviously, it has many jackets and protectors and so on. Sometimes they send the power with the cable. So the power can make 3,000 kilometers because you're not sending data over the power line. So that's easy. Yeah, obviously, right? And then that you can power the EDFAs, amplifiers, and repeaters along the way to do that. But you can imagine if something like that breaks, it's a massive problem.
But that's what I'm saying. Even to send the power that distance is a pain in the ass. Trust me, it's a difference, but weight. But they don't have to care about buoyancy, I guess, whereas we had to care about buoyancy. So there was a trade-off between your power consumption versus the weight of your copper to carry the power. And it was whereas these ones just sink to the bottom, I guess.
They go and they're well protected. But those the ships that carry those wires back, those things are enormous. And as they go forward, they obviously unload the cable at the bottom of the ocean as they travel across the ocean, and they have to take in water. Otherwise, the ship is too buoyant without the weight of the cable. It'll just topple over.
Oh, really? Exactly. I know.
It's a crazy investment. Again, it's money driven, right? It pays to do that, so they do that. We do anything that's money driven, and sometimes money is fear driven, but mostly money driven.
Right. Is there anywhere else you would rather, you dream about working?
Well,
or is Bell Labs sort of like the pinnacle worldwide of this sort of stuff that you're working on?
Well, there's one of the things that I also wanted to do is just to be a full-time professor, to do research at a state-of-the-art university, and have students and so on.
Right.
That's also really really interesting and exciting endeavor for sure. And one of the reasons I chose Bell Labs is because it is in a way similar to that, and also to get a professor position at one of these great universities that does millimeter wave research is extremely difficult. I mean, it's almost impossible. The people who work...
okay. Is that because the standards are so
it's extremely
ridiculously
competitive,
high?
right? It's extremely...
Yeah, it's like a pyramid scheme, right? Where it's like there's only so many professorships at the top.
Yeah, I mean, how many
there's
professors...
lots of grad students.
Yeah, exactly. So you don't need them, and then they're very, very good at what they do. So that's one of the reasons. But I always kind of joke about this. I said that if I ever won like a ridiculous lottery, something like $300 million, something ridiculous, like this Powerball, whatever it is in the US that they have. Not that I play the lottery, by the way. Don't play the lottery.
No, play the lottery. Chris and I, no. See,
I don't play the lottery.
You guys don't get it. You're not buying the odds. You're buying the dreams.
Yeah, of course.
Whatever,
Dave.
Dave.
Each week I can dream about it. You guys can't, right? Because I'm in it.
Whatever,
right?
man.
You guys can't even dream about
I
it.
dream every time
That's
I buy a
what
beer.
you're buying.
Yeah, that's true. No. I mean, of course, I understand that it's an entertainment value from the experience. There's no doubt about it. But the statistics are you know better than anyone what the odds are.
Of course. I know the statistics. Of course. I'm not buying the odds.
No, I appreciate.
I'm buying the dream.
If I do win something like crazy like that, or I had that much money, I would open a research center. I would hire great researchers, and I will tell them do whatever you want, and pay them very competitively to all the other places. Just make whatever you can make, and then whatever you can make is now available for free to humanity. It's everybody.
Do you think that would work?
Here.
Do you think that would?
I am sure somebody will find a way to.
It works until the money runs out. It works.
I just mean like because the motivating factor. I mean, that's really interesting. I would love that idea. I think that would be really great. But I think that that's always interesting too, because I think Bell Labs historically, right? I mean, like there was a ton of innovation there, but it was also lots and lots of money behind it as well, and it was scale as much as anything else, right? I mean, like that was.
But they didn't just give it to humanity.
Yeah, I mean, it was patented, and But
exactly.
I think that the problem that you may run into a scenario like that is that I think other manufacturers and other companies that do this will complain that you're playing an unfair game in a way, because you're putting them out of business in some way. So what I'm saying is extremely idealistic, right?
Well, tough.
Of course, yeah.
Tough.
No, I love it. I think that's great.
I mean, what I'm saying is so quixotic and so idealistic. It's just obviously has tremendous problems.
Fool.
No, I was more asking about the human nature aspect of things. I mean, like kind of more of a question of what drives us and stuff like that. I think that people like you are very driven by curiosity, right? But then there is always that the money aspect, right? That's still part of it. I mean, that affects all of us, I think. So it's just an interesting question.
Yeah, and I completely appreciate the difficulties that goes into the practical difficulties that goes into really just generating knowledge. Obviously, there's a lot of it's nice to think about it in an idealistic way, but there's limitations, and I appreciate that.
I think you would. The classic example here is the Bill Gates Foundation, right? The Bill and Melinda Gates Foundation, right? He's given away his, $300 billion or whatever. But have you seen his corporate headquarters? It requires they had to build a dedicated building. They hire thousands of people just to give away money.
It's a very complex.
Right? It's actually that complex. It's that complex.
I know.
So, in the end, you might find, this started out as a good idea, but it's actually not practical because it's just so involved to organize all this research and give it away.
Sometimes I feel like I get very frustrated with some of the systems that are in play, especially in the United States. And I'm not sure if it's because things are getting worse or I just simply know more of what is going on. And that's why it makes me frustrated. But just some of the decisions, the government makes, some of the disparity in resources that's available, how much of the recovery that the United States has done has gone to the top 2% or 1% of the population. How the system is so well geared for really rich people to tell the middle class to blame the poor people. It's just so well oiled. This machine is so well oiled. And I don't know if it's because I'm just becoming cynical because I know more about it, or is it just really getting worse, or is it getting better? I know that humanity is getting better, obviously, but
no, it's not getting better because you Yanks, sorry Chris, but didn't you just pass a spending bill, $1 trillion spending bill that on 4 pages from the end it says we're going to allow people to put money into politics. We're going to increase that tenfold.
That's crazy to me.
Yeah.
And they just snuck it. Yeah. So now you can give almost unlimited money to the politicians to buy the system even further. So instead of scaling it back, no, it's getting worse.
It's probably one of the worst things that's ever happened to the U.S. politics is the idea of being able to.
Money in politics.
That kind of defeats the purpose, because the whole point is not to have that advantage. I don't know. Maybe I'm naive and I'm being simplistic, but come on. I mean, what did you expect was going to happen if you allow that? I mean, what did you think was going to happen? All these extremely rich, powerful people are going to say, no, we're not going to do that because it's unethical. Of course not. I mean, but anyhow, that's a whole different story.
Well, and it stinks too, because I'm sure that, you see the effects of funding then being, because then on the other end, it's like, if that money goes away, then that money doesn't go towards research, that doesn't get, keep pushing the industry and stuff like that as well. I think when you're on the research side, you see that as much as anything else, because like I know I have friends that work with the NIH and stuff like that, and one guy's just like, yeah, that money's just gone, man.
Yep.
And that drives a lot of progress.
Yeah, I mean, if you look at it just fundamentally, again, I don't want to take this into a political direction, but if you think about it fundamentally, what is the main three things a society should do in general, right? It should be able to keep its people healthy for free. It should be able to educate its people for free, and it should not have its legal and prison systems for profit, right? I mean,
totally.
Those three. Those three decisions to how to run the society are fundamental to the health of the society. And none of those are true. I mean, it's terrible. And there are people, by the way, I'm talking about just from what I understanding of the United States system, but there are many countries who accomplish that quite well, and they're doing quite well indeed.
I think you used to live in one.
Yes. I mean, exactly. That's one of the great things, and in many good places in Europe as well. And that's true. So there you go. So you have to appreciate the importance of those things for your people. I understand. Again, these are very complex issues, and there are no straightforward answers to them, but there should be a striving force.
Well, there are, but except when you've gone down the path of no return.
Yeah, it's very hard.
That's when it gets complicated, which the US has.
The thing about our species is that it's very hard to take something back once it's given. All right, but it's very different. It's very different to never give it. But once you give it, it's very hard to take it away. And this relationship is not both ways. It's not symmetric. It's a hysteresis there. So you gotta watch out for that. So
Oh, I love it. Well, thank you very much for joining us.
Of course, it was a pleasure.
Awesome.
Yeah.
And for the record, how do you pronounce your name?
It's Shahryar.
Shahryar.
Yes. Perfect.
That's how I thought it was.
No, it wasn't.
But
Don't worry.
We won't repeat what Dave said when he signed on. I don't even know. I couldn't even repeat it.
Shahira.
Yeah, that's what it was.
Shahryar. It's a silent H. Second H.
If you were to pronounce it, strictly in the Persian accent, then you pronounce the H. But I've given up on that a long time ago.
Oh, okay, right, interesting. All right. So come on, tell us, how would you actually say your name
if you were to say it in Persian, it would be Shahryar.
Oh, cool.
Yeah, it's quite different. But like I said, I've been called every possible pronunciation of those letters together.
I've been called everything under the sun too, and my name's easy.
So you had mentioned the difficulty with finding potential hires.
Yes.
Is there
Absolutely.
Is there any skill set that should contact you? Is there?
Yeah, I mean, I didn't want to use this to somehow benefit myself. But
of course you can.
We love that, yeah.
Like, are you after maybe someone who's not a researcher? Do you need lab assistants, technicians, that kind of stuff?
It's difficult for us to get headcount to be able to hire. So we would like someone who has a PhD degree and someone who wants to do research and strictly speaking, kind of you have to have a PhD to join Bell Labs, but you can also have a master's degree, and that's also acceptable. But yeah, someone who can do
a lowly master's degree, just like on the Big Bang Theory.
I don't.
Poor old
I don't mean to devalue the degree at all. I mean, bachelor's degree is also quite valuable, but it's just that because it's research, so you have to have experience writing a thesis and doing research. That's really the reason for it. But someone who can do high-speed millimeter wave design, high-speed analog circuit design, who has experience, with state-of-the-art CMOS or silicon germanium process. Yeah, just that kind of expertise. Yeah.
So all those who have flashed a lead with an Arduino, apply straight away. You're right up there.
Well, no, I think another good question too is that you said you look at certain schools. So which schools, if people were, I mean, because I'm sure that we have younger listeners as well that would be like, yeah, I want to do that. Where should they look? Where should they look for programs?
I mean, my old university in Canada is a good one. Universities in the United States, Columbia University in New York, University of Southern California, University of California, MIT, all those places that have a millimeter wave, high frequency analog ASIC design team. Those are all really, really good universities. Those are obviously, I named the best ones, but there are many places that you can get your degree from and do high-speed circuit design, of course. It's just those ones are the main ones.
Don't think there's one here in Australia. I'm probably talking out my ass, but I'd be surprised if there is one. But there could be.
I'm trying to remember if I remember a publication from, let's say, University in Sydney or something recently, but I don't remember.
Maybe the University of New South Wales would probably be the only one.
Yeah,
sort of, because they do lots of ASIC.
Yes. I know that you guys do. You do a lot of system work. So there is papers coming from the system perspective, but from specifically ASIC design, there probably is. I just
I doubt it.
Yeah, that would be my suggestion. But anyhow, no matter what you do, go in it with a sense of curiosity to have the learning be its own reward. Yeah, don't think about the job and the salary and so on. Not that that's not important, but yeah. Go with that intention.
Yeah, man. Every day you don't learn, you're not alive, right?
Yeah, there you go.
you did.
That's a great message. I love that.
That's it.
Cool. Well, thanks again. We really appreciate it.
Thank you. Thanks for having me. It was a blast talking to you guys.
All right. Thanks, mate. See ya.
All right. Take care.